did have the same circuit here, except I'm going to connect this with a wire. Sometimes you see things like this appear. How do we handle this? Things like that. Or you might even see a resistor here, actually. So either a wire or maybe some resistor, 30 ohm resistor or whatever. So how do we handle that? Well, the general way to handle this is to put here some resistor. You could even call it R, and kind of do a general, do a general R function, and then analyze what's going to happen. And then at the end, set R equal to 0, because if you have simply a wire, that would be equivalent to having a resistor of resistance 0, you see, or at least close to 0, right? So you can just put some resistor there and then analyze it that way. So then how would we do? This would be I1. Remember, this one we called I2, and this one we called I1 minus I2. Then I can call this one I3. Then, so what's going to happen is I2 is going to come, and I'm going to call this guy I3, and then this one here will be I2 minus I3.
Professor, quick question.
Yeah.
If we're assuming that wire in the middle is just a wire, wouldn't the 10 ohm and 40 ohm resistors just be in parallel?
Well, what I'm going to do is treat it as a general resistor, so we are able to handle if that is a wire versus it's an actual resistor. Then at the end, we can then say, okay, now what happens if it's a simple wire, or what happens if it's an actual resistor?
Oh, so like a general formula then.
Yeah. See if we can, in other words, see if we can come up with a general formula for it first. Okay. And then from there, go to the specific cases.
Cool.
Yeah, so then here's I3, then I2 minus I3, and then what's this gonna be? The one going down this way. So if I3 comes, it will join that guy, and then here you will have I1 minus I2 plus I3 going down this way. Or I could have called I3 going to the left. I could have said that's I3 to the left, and then this would have been I1 minus I2 minus I3. But then if it goes to the left, this one would have been I2 plus I3. The I3 would have joined with the I2, and then you would have gotten I2 plus. This would have been plus, and then this would have been minus. So either way is okay, but then the current here would have been to the left. Okay, then the I1 minus I2 come this way, I1 minus I2 plus I3, and then I2 minus I3 join with that. And then what do you get here? If you did it right, you join this to that, what should happen? I2 plus I3, you join that with I2 minus I3. Okay, and then the I2 should cancel the I2, the I3 should cancel with the negative I3, and then there you have it, I1, which should be the current on this side, should be just I1. You see, so when you do all these currents, you should end up getting that back to the original current. Okay, for this one, I need 3 loops, right? I could do 1 loop. I could always start here if I want, and then just go 1, then do the whole thing. Let's see here, 1. Let's just do that first. 20 minus 30 I1, then go down here, minus 10 I2, then go down. Well, this one doesn't matter that it's I2 minus I3 because the battery, you just lose negative 10 either way. So there's no other resistor here. So then that's it. So that equation didn't actually change. you just ends up with 10 is equal to 30 I1 plus 10 I2. And then you simplify that. So then you write 1 is equal to 3 I1 plus I2. And then you have 0 I3. So nothing with the I3. So remember, there's 3 unknowns, and the I3 is one of those unknowns. So here's my first equation. Okay, and then the next one is going to be the whole, I can do the whole thing. That'd be, yeah, that's going to be good here. Let's see. 20 minus 30 I1, that's this one. Then you go down, negative 40 I1 minus I2, negative 20 I1 minus I2 plus I3. You see, so then you're going to have the zeros cancel. 2 is equal to 3 I1 plus 4 I1 minus I2. Plus 2 I1 minus I2 plus I3. All right, and then you're going to have here 2. So 3 I1, 4 I1, and another 2 I1. So then that's 3, 4, 7, 9 I1, and then negative 4 I2, negative 2 I2. Hold on, yeah. This is negative 4, and then negative 2, right? So negative 6. Negative 6 I2. Then for I3, you just have 2 I3, right? That's it. Okay, that's my second equation. I'll put it under this one. Okay, now my third loop, what should I do? I could probably do like this one, or I could do this one. If you want to, you don't necessarily have to have a battery in there. You could just simply do this one, but I think this one is harder because there's more resistors involved. Let's just do this one. It's easier. Okay, so I'll start here and I'll go this way around the loop. So here I go this way from negative to positive, I gain 10 volts. You see? So you don't look at the direction of the current flow for the battery. You just say, I'm gonna go around the loop this way. So I'm gonna go from negative to positive. So I'm gonna gain 10. This was the second loop. This was the first loop. So I'm gonna gain 10. Okay. So let me put it this way so you can see. So I'm gonna gain 10. Then over here, I'm gonna lose RI3 minus RI3. So I'm gonna go from the negative to positive. So I'm gaining, and I'm losing when I go around with the current. Then I'm also losing here. Negative 20 I1 minus I2 plus I3. Okay, so then that's equal to 0. Okay, so then what's that going to be? 10. So this one is 20 I1 minus I2 plus I3 plus RI3. Right, so then you're going to have here, okay, I'm going to put it here. 10 is equal to, okay, so 20 I1 is by itself. And then minus 20 I2, 20 I2. And then here I've got 20 plus R I3. 20 plus R I3. Right, 20 I1, negative 20 I2, 20 plus R. You might be able to do this on the online. Let's see if that works. I'm not sure if this website doesn't look that. Let's see, can this do a variable? Let's see if this website can do a variable. Calculate. Sorry, I don't know how to solve this. Let's see. How about this one? Oh, let's see here. This one is saying they can do complex stuff. Oh, I like this one. You could do very complex. They don't necessarily have to be linear. I wonder if this one can do, let's say, something like x plus ry equals 8, 2x minus 5y equals 7. You might say, no, I don't recognize that. Well, yeah, it did give you. It didn't give up that easily. It went ahead and solved it based on whatever the R is. Okay, let's try this one. So what would we put here? 3x, right? That's a 3I1 plus y plus, well, I could just say 0, right? So it's just equals to 1. Where the z would be the I3. Then the other one is 9x minus 6y plus 2z equals 2. Right? The third equation. 20x minus 20y plus 20 plus r z equals 10. Oh, then you can kind of see it nicer way right here. I enlarged it so you can see it better. 9x, yeah, 20x minus 20y. Oh, okay, here's the solution. So I1 is equal to 4 2r plus 25 over 27r plus 380. I2 is equal to 3R. The third one, the Y, is the I2. 3R over 80 plus 27R plus 380. I3 is 170 over 27R plus 380. Oh, it says R cannot be negative. Well, R cannot be negative resistor anyway, so it doesn't matter, right? Now, how do we know if our general answer is right? One way we could quickly check is take the limit of this as R goes to infinity. Remember, in the earlier example, we did this case without any wire here. We just had these two, nothing connected. So that means actually it's like having a wire with infinite resistance. You see, not being connected is equivalent to connecting this with a very, very, very large resistor. So what would be the limit of this as R goes to infinity? See, these two would dominate, right? When this goes to a very large number, these two would dominate, and then they would approach that. And then the R would cancel, and then you'd get 8 over 27. So I1 would be 8 over 27. I2 would approach what? This would disappear. So 3 over 27, which is 1/9. And then this would disappear. So this would dominate. Oh, of course, I3 would just go to 0 then. Is that the answer we got in the previous example? 8 over 27, 3 over 27 for I1 and I2. I believe so. Let me see here. Where was that? Is it in the back side? Yeah. Aha! I1 8 over 27, I2 1 over 9. You see that? So not being connected is equivalent to an infinite resistance. I'm trying to do two things here at the same time. I'm eating. You guys enjoying some lunch too? Thank God's restaurants still deliver food right to your house. That's good. Habit sandwich. I made a habit of it. Okay, now the other extreme would be to check if we connect it with a simple wire, right? R equal to 0. Then what would that happen? So then R equals to 0, this one disappears, and then only that's left. So R goes to 0, what happens? This disappears, so 4 times 25 is 100 over 380. So 10 over 38 amps. And then I2 would be what? This disappears, this disappears. So 8 over 38. And then R goes to 0, then this becomes 17 over 38. Let's see if we can make sense of that, you see. So 10 over 38, 8 over 38, 17 over 38. So then when this is just a simple wire, it's telling you that this is 10 over 38 amps, right? I2 is what? 8 over 38. 8 over 38. And then I3, let's see, I3, this one is 17 over 38. So that's weird. Like you would think a wire wouldn't have actually current going through it. No, it does, you know, just because it's a wire with no resistor. So then this is 17 over 38. So here's the conclusion. Let's just draw it here so we can see. This is 20. So we have here 10 over 38. This one here is, I'm just writing the currents now down, just so that we can see what's happening. This is 8 over 38. And then this one, 17 over 38. And then down this way would be what? I1 minus I2, right? Yeah, that one we called I1 minus I2, which would be this minus this. So it'd be 2 over 38. So you see 10 over 38 comes, then you got 8 over 38, 2 over 38, and then what would be this guy? And we have a battery like this. So I'm trying to see if really we could make sense of it. And then this is going to be what? These two join up. So it should just be 19 over 38. And then 19 over 38 comes like this. Then what should that be? We called that one I2 minus I3, right? It was I2 minus I3, this minus. Oh, so actually the current is going up this way. You see? So what should that current be? Well, like you could say, what current do you need here so that when joined with this gives you 17? Do you see? So at the end, it's always nice to kind of draw all your currents. In the previous example, I drew all my voltages. Either one, but at least I think currents are really helpful because you can kind of also see, oh, at the end, what is the direction of flow of the currents and try to make sense of that. So you got 19 over 38, 19 over 38. And then this one, it should be what? What do you need to add to 18 to get 7? 9, right? 9 over 38. 9 over 38. So 9 over 38 amps is going this way, joining with 8, then giving you 17, and then 10 is coming this way, then splitting and giving you 2, and then 17 is joining with 2, giving you 19, and then what's happening to the rest of the 19 here? 19 minus 9 gives you what? Oh, yeah, the 19 minus 9 gives you 10. Which it should give you because the current here should be 10. Oh, okay. Wow. Okay, now the next question will be, can we have guessed this answer without doing the full-on loops? I guess that's what you were trying to get at, Daniel. You were trying to guess this answer without necessarily doing the Kirchoff loops.
Oh, so yeah, sort of. I mean, because something I guess we sort of see is that wire in the middle is still part of the same node, basically.
Okay.
And so since that's just one node, those two resistors that are above that wire are in parallel, pretty much.
You're saying this and this are in parallel?
Yeah. Yeah, like you could rewrite the circuit to have those be in parallel, and you would get. I mean, and the only drawback is that you wouldn't be able to get that current in the wire.
Oh, yeah. With your technique, you wouldn't be able to get this?
Yeah, you wouldn't be able to get that doing that, but like other information pertaining to the resistors, yeah, you could.
Oh, so you're saying what was the resistance of this? This was resistance of 10, right?
Mm-hmm.
And the resistance of this was what, 40?
Yeah.
So what Daniel is saying is, if you multiply this current by that resistance, you get 80 over 38, and you multiply the current of this by that resistance, you get 80 over 38. So the voltage drop here is the same. So he's right. So by the time you come to this point, if I take a voltmeter and place it across this wire, it's going to be zero. No difference of voltage. So even though there's current here, because it has no resistance, there's no voltage drop. So then these two are in parallel, and then these two are in parallel, right? So if this is, what was the resistance of this? 20. If you multiply 20 by that, you should get 10 volts. Was that 10? Yeah, because this is a half an amp, right? This is a half amp. Yep. So based on your argument, Daniel, these two are also in parallel, right? The battery is parallel with this guy. So this is half times 20, that's 10 volts. And then this is also 10 volts. Yep, you're right. So can we use that parallelness to figure out, in other words, to figure out this answer, can we just use that? Can we say these two are in parallel and get their net resistance that way? Let's see here. 40 and 10. This is I guess I'm trying to reduce this to a circuit that looks something like this. This was a 30 ohm resistor. And then these two are in parallel. So they are, what's 40 and a 10 in parallel?
I think it's 8.
Huh?
Maybe 8 ohms.
Let's see here, 50 over 400, 40 over 5, that's 8, right? So that would act like an 8 ohm resistor, these two, right? And then this would be parallel with that, but it's just basically by itself. So it would look almost like this. You see what I mean? Can we reduce this to that? And now can we solve this without needing Kirchoff's loops? Well, let's see here. This 8 is in series, huh?
Yeah, I was gonna say there is a way you could do it, right? Because you have those two in series. Then you end up having that 38 ohm resistor. Then the two voltage sources and that third resistor are in.
Yeah, so look, that's kind of where the 38 is coming from. If you think of it, these two are acting like in parallel. So 10 and 40 is acting like an 8, plus the 8 and the 30 are acting like as a series. So then there's your 38. Let me get another paper.
Yeah, because then once we have that, we can actually say that the voltage difference on that 38 ohm resistor is going to be the 10 volts, right? because we have 20 volts on one side and then 10 volts on the other. You can actually get the current on that.
Let's
part
see.
of the circuit.
So then it's behaving like this. 20, and then you got a 38, right? And then you got then it splits into 10 and 20. Like that. And then what would you do?
Yeah, the way I would have drawn it, here I'm gonna annotate real quick. So yes, we have like we have our voltage source, right? Then
Yeah.
Resistor.
You want to share your thing?
No, I think it's fine. I don't know if you can see what I'm drawing right now.
Oh.
Okay, so then we have our.
Oh, you're sharing on my thing. Oh, nice. Okay.
Right. So then we have a 20 volt here. At 0. And then our 10 volt here, right? And
Okay. So you're redrawing it with the 10 and the 20 in parallel.
Mm-hmm. Yeah, because then that means like, okay, so if we set this bottom, because again, all voltages are relative. So I ground the bottom, right? So this is my 0 volt point. Then we say that, okay, then at this point up here, right, we're at 20 volts. At this point over here, we're at 10 volts. So the difference on that 38 ohm resistor is 10 volts, right?
Yeah. Okay. So then you just take the difference of that.
Right. Yeah. Then that makes the.
10 over, that's what we got, right? 10 over 38. Oh,
Yeah.
okay.
Yeah.
And then how would you get the voltage of the 20 ohm on the right?
Well, just using the same thing, right? Since we know that the difference here is 10 volts, the difference on the 20 is also 10 volts, right?
Okay. Then you would do 10 over 20.
Yeah, and that gives you 0.5 amps on that guy. And then you can probably work your way backwards to the other one, right? Without really having to touch like the Kirchoff rules so much.
Yes. In other words, you're saying with this technique, you could kind of say, okay, R is 0, like the way we did, and then reduce it down. Okay, basically, it kind of comes down to saying this R here. When this R is 0, these two parallel and these two are parallel. Forget about the current there. And then these two are parallel, you get the 8. Mm-hmm. And then the 8 and the 30 is 38. Then it reduces to this. And then like you can say the arguments that Daniel is making and go from there. With my technique, you don't really have to so much worry about that.
Yeah.
You can kind of say, okay, set it up as a general answer. It's probably be a little bit safer, right?
Yeah.
Where you just say, okay, I don't really have to worry about which one parallel, which one, whatever. I could set it up as a general resistor, do my loops, get a general answer, and then I could apply it to whatever the R is, no matter what, and then set it equal to 0, and you don't have to worry about all of that. So that's how Kirchhoff's loops really help in this case.